All right. Well, thank you for joining the second half of the talk. I might move a little bit faster. So we ended with this idea that the flows in the torus that are super dense are exactly the ones where the slopes are these badly approximable numbers. Really, I should have attributed maybe the definition of superdensity above to Beck and Chen, which is they had a paper who that motivated the result that I'm going to be talking about. So let me give you the theorem that that they proved. So they extend Khinchin's sort of very classical result, and they extend it in this very classical way, which is really cool, using sort of in some sense very classical number theory type tools. So they proved that. Well, let me write the theorem, and then I do need to maybe say a little bit about it because I'm changing it slightly. But they did prove it. Okay, so what they showed was they essentially took the result and extended it to square-tiled surfaces. Here, we'll just say these are translation surfaces, a special kind of translation surface. This is tiled by squares. Okay. And the reason why I kind of paused earlier is because they do prove this are square-tiled surfaces, but they also they kind of, their starting point is a surface that's tiled by squares that adds these additional sort of things that you can. So maybe it's kind of tiled by squares like this, but then there's a special kind of wall right there, so the trajectory could maybe bounce off, kind of do something kind of like this, but with some kind of unfolding procedure, we can kind of recover a square-tiled surface. And so yeah, so what they did was they extended this to square-tiled surfaces, or maybe a little bit, potentially a little bit more. They call these polyregion surfaces. I think if you're interested, and they have a definition in their paper. But what interested me was the square-tiled surface, because you could sort of wonder if the same types of properties are true on all sort of translation surfaces. And so let's see. I do need to give maybe one quick thing. So it hasn't come up yet. So the quick definition. So the geodesic flow, let's call this the Teichmuller geodesic flow that's referenced in the theorem, which I'll write again in just a second. The Teichmuller geodesic flow is the one parameter subgroup of SL2R that looks like this: e to the t, e to the minus t. So what this does is as you continue to hit your surface with this one parameter subgroup, it compresses the y directions exponentially in time, and it's stretching the x direction. Okay. And so it turns out that there's on the torus, there seems to be this relationship between boundedness of sort of a geodesic inside of the moduli space and choosing that initial direction to be badly approximable. And you can, there's a connection to continued fractions there. And so that sort of motivates this idea of, well, if we look at the moduli space, do we see more bounded geodesics for things other than tori, maybe square-tiled surfaces, maybe more than that. So I don't have a complete answer for you, but the theorem that I will say, it's kind of reminiscent of something like Mazur's criterion, if you know what that is. The linear flow on omega is, I don't want to do it like that. Let's do it like this. The type Mueller geodesic for t greater than 0 is bounded in the moduli space. So if this is true, then, so we have some property of the moduli space, which seems to be controlling something down on individual surfaces. Then the linear flow is super dense. Okay, let me prove this. The proof technique is using a kind of renormalization. So if this geodesic, so we're in some kind of moduli space. I'm not exactly sure what it looks like, but if this geodesic is bounded the way that it's moving around, then it lives inside of some, compact set I'm going to call K. So GT omega is living inside of this compact set. And if you think about the diameter of the translation surface, if you nudge this a little bit using a very, like a matrix that, doesn't move the translation surface that much in the moduli space. So if you take a linear transformation that just kind of nudges it a little bit away from where it's at, the diameter of the surface shouldn't change that much. So the diameter is a continuous function on the moduli space. And so that means that the diameter of GT omega has a maximum. Okay, let's call it d tilde, and then let d be essentially the diameter, but just add a little bit to it because we're going to use it to cover. Okay. So this delta is just something very small. And so now what we're going to do is we're going to start using this renormalization technique. So I'm going to start with kind of a picture that kind of describes what's happening. So I'm going to take kind of an arbitrary point in space. And I should say we can't run into a singular point. So it has to be a leaf in a foliation that's not going to run into a singular point. So maybe I take a segment that looks something like this. So I have some geodesic segment on the surface. Let's say the length of the geodesic segment we're going to make it d times t, and this is going to be for any t greater than 0. So I'm just going to go out some amount, some t, but we're gonna do d times t, where d is essentially the diameter of the surface, and the diameter of the surface is what we're going to use to kind of control superdensity in some way. Okay. So now let's apply g log dt. And so what does this look like? So remember, gt was this e to the t, e to the minus t. So log dt would just be a dt and a 1 over dt. Okay, so it's going to stretch this in the x direction and compress it in the y direction. And we're going to end up with a geodesic segment over here that's a little bit shorter. And just notice the length of this geodesic segment is now 1. Because the geodesic segment is just in the north direction, so I took the geodesic segment that was dt, and then the vertical direction compressed by 1 over dt, and we're left with a length of 1. And it turns out that I could put like an epsilon here, or an epsilon for the length. It doesn't really change anything. I just need something after I apply. I need some amount of length, over here with the after I apply the geodesic flow. So I flow out by log dt. Okay. Now let's call this geodesic segment over here. Let's call this segment L1. Okay. So now what we're going to do is use what we know about the diameter. So since g log dt times omega, which is the picture on the right, so it's along this trajectory, so it has a bounded diameter. I can find a neighborhood around the trajectory I'm going to call u, which is essentially x inside of this translation surface g log d dt omega, where the distance between x and L1, the trajectory in the image is kind of less than d. Okay, so I can take a neighborhood that looks like this, since the surface has this bounded diameter, and I made d just like a little bit bigger. U is going to cover this translation surface. Okay, so in some sense, so now we have this u, and the purpose of this u is to give us sort of a handle on some dimensions inside of the translation surface. So we know that this shape, whatever this is covering the translation surface. And so now what I'm going to do is I'm going to go backwards along the geodesic flow to where we started, and then I'm going to look at the image of this cover under the inverse bend, right? So we're going to apply g minus log dt 2 g minus log or plus log dt. Omega, which is covered by u. Essentially, we're kind of applying it to u, but I mean, we're applying it to the translation surface. It just happens to be covered by this neighborhood. So we're going in the other direction. I'm going to do it like this. We're going to take our little segment L1, and then maybe we have a large neighborhood. This is my u, where these distances are all d. Okay, so I have this big neighborhood. And now I'm going to apply g minus log dt omega to this picture, and we're going to end up with, well, the old trajectory that we had, and then something, well, we're going to end up with something kind of like this. Okay. Okay, so if we think about what this is doing, so this matrix is 1 over dt, 0, 0, dt. So when we go backwards, we're now expanding in the y direction and compressing in the x direction. And you can sort of see that, let's see, what will happen. The x direction, which was d, over here is going to become divided by a dt. Okay, so this becomes 1 over t. Okay, so great. So we have a neighborhood that's kind of 1 over t, and we're heading towards the definition of superdensity. There is something a little unusual at the top here and at the bottom. So that length started as d, but then it multiplied to become like a d squared t. Okay, and so what we're going to do is we're just going to stretch the this segment just a little bit further. So let's say it like this. We're going to pick, say, C to be, let's say, how about the original length of this segment was d times t. And let's see. So we're going to pick d to be c to be dt plus d squared t times. Okay, yeah, just that. So let me. So what am I doing? I'm sorry. We are extending. We're going to extend the original segment to include the green pieces. So we started with a segment that's dt. I'm going to extend it to include these green pieces. So this is the kind of the new length of the segment. And so that's not t or c. Sorry, let me back up. We're just going to extend that original segment. So we have a new segment which has a length dt plus d squared t. Okay, and so just notice that the length of the segment, we could write it as d plus d squared times t. And we can imagine this is t is flowing along the segment from 0 to this point. And so we're saying we need to pick c equal to d plus d squared. We can sort of see how the square of the diameter is the thing that's really controlling this. Okay. And when we do that, that segment is going to be within 1 over t of every point on the surface. So this segment is 1 over t dense. Okay, and so that completes the proof. Awesome. So you might wonder if the converse is true. I don't have a proof with converse. And in fact, there's a few things that I can kind of show. So I will, I'll do that. Maybe I'll write some of the things that we can show. So if the linear flow is super dense, then GT omega has bounded diameter for all t greater than 0. So again, we have to sort of not run into the singular points in the geodesic, but as long as that's not happening, then any GT omega yeah, so the super dense flow that we're interested in, we just have to find one on the surface that's not hitting a singular point. And then we know that GT omega has to have bounded diameter, but unfortunately this is not good enough at least I don't, it's not good enough in the moduli space as a whole. So it's not necessarily like the compact sets have bounded diameter, which is something that kind of messed me up a little bit. But I think this might be something that's true along the geodesic, but not sure. Not sure. So I don't have proof of that. Let me give another lemma, something else that we could show. So if the linear flow is super dense, then for any t greater than 0, maybe I'll write it like this. So we can't have a saddle connection. The saddle connection would be, say, I have a singular point on the surface. A saddle connection is just something that connects singular points. Okay. So we can't have a saddle connection. I'll just say it like this: degenerate, or the length of the saddle connection go to 0, and that's well, we should, for the sake of the talk, we should add on say a lattice surface. And the reason why is because if you have a saddle connection that's sort of degenerating under this geodesic flow, it's vertical, which means that you have a cylinder next to it on a lattice surface. And you have a closed trajectory, and that's the first example that I gave of something that's not super dense, right? Closed doesn't really work. You could try to extend this, so you can't extend this to a larger class of translation surfaces by using some things that Alex Wright proved. In particular, if the translation surface is living inside of this rank 1 affine invariant kind of submanifold. But so you get sort of the same property with the cylinder. So what's kind of interesting is that which I'm not quite sure how to do, but might be interested in, all right, can you have the length of the shortest saddle connection going to 0? And I don't think that you can, but you have to deal with the this situation where you could have a sequence of saddle connections that are kind of getting smaller and smaller, and then they stop getting smaller. But then here comes another one that's getting smaller and smaller, and it's approaching zero a little bit more, and then it doesn't go to zero, but then the next one is getting closer and closer. And in fact, this is kind of interesting because in talking to somebody recently, it seems like this is somehow connected to the numbers which are not badly approximable. With some kind of continued fraction. So I don't understand this entirely, and I'm trying to wrap my head around it. But anyway, I'll stop there, and I'm looking forward to your questions, or just if you want to chat, happy to talk about this work. Cool. Thank you.